Alright, so I want to welcome all of the Professor Miller. My email contact information is over there. This is probability. This is a 300 level math class. Normally I work with students far harder than this, but since this is a visiting day, we tried to tone it down a little bit. So we're going to just do division. Alright, so this was actually one of the problems on the first real homework assignment. I've multiplied by 1,000 just to make things a little bit nicer. Divide 1,000 by 998,999. And if you do this out, it takes a little bit of time to actually use an environment that will display this correctly. You get 0.001, 001, 002, 003, 005, 008, 013, 021, 034, 055. It's so easy to make it now, lecture. 089, 144, 233, 377, 610, 988, 588, dot, dot, dot. Alright, so for one of my visitors, I'm going to put you on the spot. What number does this look like?
Fibonacci.
The Fibonacci's. It doesn't stay Fibonacci's forever though. It does break down at some point. But it's remarkable how long this stays as the Fibonacci's. And so what I want to do today is I want to talk a little bit about why relationships like this hold, what's going on here, what's the mathematics behind something like this. And it turns out that what's really lurking in the background is what's called a generating function. And we're going to use generating functions up the wazoo when we get to the central limit theorem later in the semester. But right now, this is going to be a little bit of a mystery as to why we care so much about generating functions. Obviously, whenever you have a division like this, somebody has spent a lot of time choosing the problem to make it look nice and interesting. So I want to start off with the Fibonacci numbers. So fortunately, it seems like everybody has seen the Fibonacci numbers. I'm going to show you an interesting application to a generalization of the Fibonacci numbers. I'm going to show you how you can use the Fibonacci numbers to learn not to do certain types of gambling. Okay, when you go to Las Vegas, is it advantageous or not advantageous to gamble? Not. Trust me. They have people there who study these problems very hard. These probabilities are carefully assigned. When you're playing poker in the dorms, or something like that, is it advantageous or disadvantageous to gamble? Depends who you're with, right? Be careful who you're with. But there are some people who do not know math, who do not know probabilities well enough. You can take advantage of them. Disclaimer, I am not, of course, advocating you taking advantage of people who are not as math prepared as you. But there are situations where you can use that to your advantage. Vegas is not one of those places. They have calculated these probabilities very carefully. So what I want to do is I want to show how a generalization of the Fibonacci numbers leads to understanding some of these games of chance. Why do we care about games of chance? Well, part of this is just being historically honest. Probability really arose from people studying games of chance. If you think about who's going to fund you, who's going to care about your results. When you're trying to make money, there's interest. All right. So we have the relationship fn plus 1 equals fn plus fn minus 1. And we'll start off with f0 equals 0 and f1 equals 1, and then we get the sequence 0, 1, 1, 2, 3, 5, 8, blah, blah, blah. Later in the semester, we might actually look at other ways of defining the Fibonacci numbers. This turns out to be a really good definition for most of what we're doing. There's some other advanced stuff where this is not the right way to define the Fibonacci numbers. We actually define the Fibonacci numbers as just 1, 2, 3, 5, 8. All right. Is it hard to calculate the 10th Fibonacci number? How about the 1000th Fibonacci number? We have different notions of hard. I don't consider it hard to calculate any Fibonacci number. Just propagate down the recurrence relation. How about pleasant? If I told you your grade depended on your calculating by hand the 100th Fibonacci number or the 1000th Fibonacci number, you may not enjoy it, but in terms of difficulty, I might have an email from the dean waiting for me. Their probability grade is due to what? It's just basic algebra. It's just addition. Okay. So if all we care about is calculating the numbers, it's fine. If we care about calculating it quickly, the recurrence relation is slow. So recurrence relation solves or gives the sequence, but it is slow. And so what I want to do is I want to show you a better way to calculate the Fibonacci numbers. How many of you have heard of Benets Formula? Okay. I should probably phrase it as, how many of you have taken a class with me and not heard of Benet's Formula? All right, so this is something I try to work into almost all of my classes. So we seem to be losing the pivot today, so I will try to fix this. All right, so Benet's Formula is a wonderful way that allows you to bypass going through the recurrence relation and just jump to the solution. So Benet's Formula. So Fn is 1 over square root of 5, 1 plus square root of 5 over 2 to the n, minus 1 over square root of 5, 1 minus square root of 5 over 2 to the n. One of my favorite ways to prove things in mathematics is the method of divine inspiration. Do you know how the method of divine inspiration works? Aha! So that's the method of divine. It's very tough to teach, unfortunately. So you write down the correct answer, and you're done. Sometimes, of course, you might then want to solve a related problem, and it might be difficult to be divinely inspired again. So we can check. If we put in n equals 0, we get f0 equals, okay, 1 minus, we'll get 0. If we put in n equals 1, then the minus, the 1 half and the 1 half cancel because of the minus sign. These reinforce, and we get 2 root 5 over 2, which is root 5, which cancels. So if we just plug in, we get f0 equals 0, f1 equals 1, and then you show that fn plus 1, using this formula, does equal fn plus fn minus 1 by algebra. So this formula satisfies the same recurrence as the Fibonacci numbers. It has the same first two terms, therefore all the terms must be the same. This is a proof of Benet's formula. This is a horrible proof of Benet's formula. It is unenlightening. It gives you no idea of where it comes from. There's a lot of things that are worth mentioning here. As n gets very, very large, in absolute value, 1 plus root 5 over 2 is larger than 1. In absolute value, 1 minus root 5 over 2 is less than 1. So when n is huge, this number here is essentially 0. So it says the nth Fibonacci number is essentially the closest integer to 1 over root 5 times the golden mean to the nth power. Incredible. The other thing I like to say is, what kind of numbers are the Fibonacci numbers? What word would you use to describe them? The integers. So imagine you have a police lineup of numbers, and you see this in a police lineup. Does this look like an integer? You've got square roots, you've got division by 2. This does not look like an integer, yet somehow everything cancels. If you want a fun exercise, what can you replace the 5s and the 2s by and still keep getting an integer every single time? All right, so what I want to do now is I want to show you how you can get to Benet's formula. Okay? And what I'm going to do is I'm going to erase this now because this was divinely inspired. We should not be able to just write down the answer. That feels like cheating. All right. So generating functions. So I'm going to define a function g of x to be the sum, n goes from 0 to infinity, of fn x to the n. So this is f0 plus f1x plus f2x squared plus dot 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 dot. It's a perfectly fine function to write down. Now, of course, one of the problems with this is we don't know what the Fibonacci numbers are. The whole point is we're trying to figure out what the Fibonacci numbers are. We're going to write down a function whose coefficients are exactly what we want to find. This does not seem like a promising approach. The reason this is going to work is we're going to be able to find a closed form expression for g of x. And this is one of the reasons why I wanted to talk about this in class. When we did the basketball problem on day 1, or day 2, whichever day we did it, we talked about how we got a closed form expression for it. We replaced the infinite with the finite, and we were able to work with that. This is one of the big themes of the class. It turns out we can come up with a finite expression, a finite polynomial for g of x. And from that, all that we want will follow. At the same time, and I know this is a lot for one lecture to do, I will also justify the least favorite technique you've ever seen in Calc 2. What is your least favorite technique from Calc 2?
Integration by parts.
No, I'm going to have to ask you to leave if you say integration by parts. There is something much worse. Partial fractions. Yeah. You talk about differentiation with proportional. I mean, who likes partial fraction decompositions? No, I'm glad you're willing to raise your hand. I like them. I want to try to justify to you why we care about partial fractions. It's usually the most hated technique in Calc 2, and it's the one we try to studiously avoid giving you in all future classes. Your integration by parts, we have to keep using that because it's one of the few things that's not so bad to do. Alright, so we have the following, but we know that even though these numbers are unknown, as soon as I specify the recurrence relation, we can calculate any of them in terms of the recurrence relation. We know fn plus 1 equals fn plus fn minus 1, and we know f0 equals 0, we know f1 equals 1. Okay? So what we can do is we can say our function g of x is the sum, n goes from 0 to infinity, of fn x to the n. I'm going to write the algebra a little bit differently. I claim that this is the same as the sum, n goes from 2 to infinity. How do I want to do this? I'll start off with something else. I'm going to consider the following. I'll go from n plus 1 x to the n plus 1. This is closely related to the function g of x we defined above. I'm starting my sum at 2, and I have an fn plus 1 and x to the n plus 1. The reason I'm writing this as fn plus 1 is I want to use the recurrence relation. Right? This is the same as the sum, n goes from 2 to infinity, of fn x to the n plus 1 plus fn minus 1 x to the n plus 1. Now what I want to do is I want to say the sum of the two terms is then the sum of each one individually. What you can do is if you've taken a class in analysis is you can justify this formally. What we can do is we can go through and at the end of the day we'll see that if x is sufficiently small, everything converges. As a quick aside, can anybody give me an upper bound as to how fast the Fibonacci numbers can grow? I claim they can't grow too fast.
Okay, they can't double.
They can't double. Excellent. Make sure you email me. Because if I replace fn minus 1 with fn, I've made them a little bit larger. So I know each Fibonacci number is no more than twice the previous. So when I go over here, when I look at the sum, if the absolute value of x is less than a half, it's going to converge. It'll be the comparison test for the geometric series. So we do know we will be okay if x is less than 1/2. The question is, how big can x be? Because the Fibonacci numbers, they don't quite double. So we could actually have x a little bit greater than 1/2. So we're not going to worry about that right now. All right, so now let's look at this. This is going to be the same as the sum, n goes from 2 to infinity, of fn xn plus 1, plus the sum, n goes from 2 to infinity, of fn minus 1 xn plus 1. Well, I notice that these are not quite correct in their indices. I've got an fn here and I have an x to the n plus 1. Let me pull an x outside. So this will then become x times the sum, n goes from 2 to infinity, of fn x to the n. And then this one, what will I pull outside here? An x squared. And I'll have an x squared, the sum, n goes from 2 to infinity, of fn minus 1 xn minus 1. How many of you have taken differential equations? If you've taken differential equations, if you remember your series expansions, how you try to find it, it's the very same technique here in terms of finding series expansions. All right, now, notice that these look a lot like our function g of x. G of x is the sum, n goes from 0 to infinity. Over here, we have the sum going from 3 to infinity. So this side over here is g of x minus f0 minus f1 of x minus f2 of x squared. Because we have the sum from f3, x3, f4, x4, x5, x5. So if we just subtract this off, everything is good. Over here, what is this sum? It looks like it's x times g of x, but we're starting at 2. So we should subtract off f0, and we should subtract off f1 of x. And over here, we're starting off at f1, so we should subtract off f0. So it should be g of x minus f0. What does f0 equal? 0. So, all right, well, good. f0 is 0, f1 is 1. So the relationship is not so bad. And so we get the following. We get g of x minus x squared equals x times g of x minus x plus x squared g of x. Does this look similar to the basketball problem? We had the probability of Bird winning, and then we just isolated for it. We used the bring it over. So I've got g of x, g of x squared. So I get 1 minus x squared times g of x equals, I bring this over to the other side. I've got x plus x squared. And then I've got a minus x squared. Yes?
What happened to the F2?
The coefficient of f2 is just 1. That's this over here. And so we get x plus x squared minus x squared. So we can solve, and we get g of x equals 1, so equals x divided by 1 minus x squared. Okay? We have a closed form expression for g. I'm not going to go through all the algebra to get to Benet's formula. I want the perspectives to actually come to Williams. I'll give you a link so you can actually see how you would finish the algebra. But we can now write g of x as x over 1 minus alpha x, 1 minus beta x. And now we can start to use partial fractions. And then when we can write this, we'll write this as, a1x plus a2 over 1 minus alpha x plus b1x plus b2 over 1 minus beta x. I'm not going to do the partial fractions. Nobody wants to see me do the partial fractions in paper. You do not want to see that. Okay? We do partial fractions and we get this. How do we expand the 1 over 1 minus alpha x? What do we use to expand that? Where have we seen something like 1 minus alpha x before? How would we expand that? Using what? Yes?
Binomial.
Not the binomial. The geometric series. If I call this 1 minus r, we would expand it as 1 plus r squared plus r cubed. So we expand this using the geometric series. We expand this using the geometric series. And when you expand it, you're going to get coefficients of x to the n from here, coefficients of x to the n here. You then just match them, and that will give you the Fn. So the rest of it is just doing some algebra. You expand it using the geometric series, and that's where Benet's formula comes from. We have two series expansions. We have the initial series expansion, Fn x to the n, and then when we use the geometric series formula, so geometric series, when we use the geometric series formula over here, we now get a new infinite series, crot sub n x to the n. They must be equal. And that's where Benet's formula comes from. So that will then give you Binet. Okay? There's a lot of stuff going on here. So I've put more time doing computer coding in class this year and less time doing the mathematical modeling. If you want to see a longer video on this, I'll give you the link to the video from last year where we go through the whole day doing this. Briefly, what's going on? We have a recurrence relation. We relate the current values to the previous values, or the next value to some of the current values. This is a depth 2 recurrence relation. All that matters is your current state and your state immediately before. Not surprisingly, the more terms you have, the more complicated the recurrence is. This is a constant coefficient recurrence relation. The numbers here do not depend on n. That makes your life a lot easier. If the recurrence relation keeps changing as n progresses, think of n as your time, it's going to be a lot harder. We have exact ways to solve stuff like this. And we have things like Benet's Formula. If you've taken linear algebra, this is very similar to what's going on with the spectral theorem from linear algebra, with writing things down in terms of the eigenvalue, eigenbasis. What's wonderful about Benet's Formula is that it allows you to bypass lengthy computations and you can just jump to the answer. So how is this related to how we started the day? I said that there's a generating function. And so if we now consider the function g of x is x over 1 minus x squared, g of 1 over 1,000 is going to be 1 over 1,000 times 1 minus 1 over 1,000 minus 1 over 1,000 squared. I leave it as an exercise to see how you get from something like this to the number 998999. That's where this comes from. That's why there's such a nice answer for this. And you can see why the Fibonacci numbers will work, because this is equal to the sum of fn x to the n. If we put in x equals 1 over 1,000, this is going to have them well separated, and the Fibonacci numbers are just going to be pasted until you get to the point where the Fibonacci numbers have enough digits that they're going to be overlapping. All right, so there's a lot of stuff that went on here. It turns out a lot of things in probability can be modeled by recurrence relations. And if you can solve recurrence relations, you can solve probability problems. There are two ways to solve recurrence relations. One is to just use the recurrence formula and just propagate and just list the stuff and go through it, one at a time, at a time, at a time. It's not pleasant, but it will work. The other thing is to write down a closed form solution. The closed form solution has a lot of advantages. One of the biggest advantages is if you have parameters in your problem, you can then sometimes see how does your answer change as you vary the parameters. Okay. What I want to do now is I want to give you an application of this as to why might we care about solving things like this. I do not know of an instance where the Fibonacci numbers will either make you money or save you money, but I know situations where generalizations of the Fibonacci numbers will. And to me that's close enough. Alright? If anybody is interested in trying this out, Foxwoods is not that far from here. We have the opportunity of choosing what we do for the end of the semester. I am happy to talk to you about card counting. We will just turn off the recording devices at that moment. How many of you have seen the movie 21 or Bringing Down the House? I forget, did they call it Bringing Down the House? Which one? What did they call the movie? 21, okay. So what's great about that is it's more than just the mathematics. There's also the psychology and how do you actually exploit the mathematical advantages you can gain. So if people are interested in card counting and stuff like that, obviously do not talk to me because I do not believe in doing anything like that, and I never would ever condone that. Okay. How many of you have heard of the game Roulette? Alright. We're going to consider a simple, okay, can somebody tell me how the real roulette game goes? Yes?
So you pick a number and you put it on a wheel and then you spin the wheel and then the ball falls into a number.
Okay, describe the wheel.
It has colors.
How many, okay, how many of each?
1. 17.
It has 18 red, 18 black, and then 2 green.
Oh, you meant that and then.
I'm in that. We're going to assume that after the 2016 presidential election, they've decided that this is an unfair advantage to Vegas. Because right now, what you would do is you let's say $1 that red comes up. And if red comes up, you win $1. If red doesn't come up, you lose $1. Is this a fair bet for you? No. The probability that red comes up is 18 out of 38. So this doesn't seem fair that Vegas gets those extra 2 greens. So the person who won the presidency in 2016 campaigned on eliminating that from Vegas. And it turns out that that became the most important issue in the election. swept them into office, and Vegas is now no longer allowed to use the greens. You now have a 50-50 chance of winning. It turns out it doesn't matter. We can do the entire analysis with 18 out of 38, but let's just assume that we now have the fair game. So this would be fair roulette. The other thing, of course, is if I can show you that you can't even win at fair roulette, the odds that you can win an unfair roulette is even worse. So here's the strategy. It's called double plus one. And it works as follows. You bet $1 on red. If red comes up, you win $1. Great. What happens if black comes up? I'm sorry? You lose $1. You're not so happy. All right, so you've now lost $1 because black has come up. So what you do is you then bet again. So $1 on red. If red, you net $1, else you're down $1. All right, so if we're down $1, what do we do? How much do we bet?
$3.
I'm sorry? Not $3. It's called double plus one. You double your previous bet. You bet $2 on red. Okay? If red, how much do you net? $1. And you smile and you're happy. If black, what happens? How much are you down? 3. So now, how much do we bet? $4. And if it's red, what happens? How much do you net? $1. And if it's black, what happens? You're down 7. Down 7. Trust me, Vegas will do the arithmetic correctly. You'll be down 7, not 6. How much do you bet next time? 8. You double your previous bet. Eventually, a red will come up, and you will net $1. Then you apply the lather wins repeat method, and you just keep doing this again and again and again, and eventually you win $1. Then you do it again and again and again, and you win another $1. Why am I not in Vegas doing this? I mean, I do enjoy teaching at Williams. It's a great place to come. But why am I not in Vegas doing this?
Is it because they put like a limit?
Oh, no, I don't want you to get into that. There's a more obvious one before the limit.
You're gonna just lose all your money on if you have one like really bad streak.
So, one possibility is you may have a couple of blacks in the beginning, and you may not have the financial reserves to keep playing. As well as, we will ignore for now the intestinal fortitude to put down, $4 million maybe after you've just lost a couple. So one solution to this is the eccentric rich uncle, eccentric rich aunt hypothesis. So I hypothesize that I have a family member who truly loves me, is extremely wealthy, and will cover any bet I need. And they will provide whatever financial reserves I need. Now they're eccentric. They will not actually just give me $1. But if I need $1 trillion to place a bet, they will provide the $1 trillion. Now in economics, this is absolutely a fine assumption to make. So again, what I want to show you is even with an assumption like this, we're not going to be able to win. For those of you who this is not an assumption, please see me after class. Okay? So we will assume that you can always cover any bet you need to. And we'll show that even in that case, you still lose. All right, so now what's the other issue?
They put like a maximum amount that
They
you can
put
bet.
a maximum amount you can bet. So if you start at $1, at some point you might need to put down $32. And maybe the table maximum is 20. And they calculate this very carefully. So the question becomes, and this is a natural probability question. Hey, good, this is a probability class. What is the probability maybe you get 5 consecutive reds, 5 consecutive blacks, and are bankrupt? Well, not bankrupt, but you have 5 consecutive blacks, you need to put down 32, but you can only put down 20. So the problem in this method is when you win small, and when you lose big. So what's the probability? What do you think the probability is that if we spin it 100 times, we get 5 consecutive blacks? you think this is a likely event or an unlikely event? What's the probability of getting 5 consecutive blacks? 1 in 32. So if I'm doing this 100 times, do you expect to get 5 consecutive blacks if I do it 100 times? Or do you think that should be safe? How many people say safe? How many people say not safe? How many people don't want to gamble? We want to calculate this probability. There are great ways to estimate this probability without solving the equation. But what I want to do now is I want to show you how you can solve this using the recurrence relation. It's actually going to reduce to a quintic. It's going to allow us to review a lot of the concepts we've done throughout the semester. Which is the easier event to calculate? The probability you get 5 consecutive blacks or the probability you don't get 5 consecutive blacks? You have a 50-50 chance. No, but it's easy to calculate the probability you don't get 5 consecutive blacks. So the probability not 5 consecutive blacks. So we'll call this AN will be the probability we do not get 5 consecutive blacks in n tosses, or in n spins. As an aside, one of the advances Vegas has done in the last few years is they now record for the public to see the results of the last few spins of the wheel. There are, to some extent, 2 types of morons. There are those who go, oh, red is hot. I want to bet on red. What are the other morons? Black is due. I'll bet on you. They don't really care which type of moron you are as long as you are willing to put your money on the table. They want you gambling. Please do not send the link of today's class to Vegas. Okay? So we're going to let A be the probability we do not have 5 consecutive blacks in n tosses. So we start here at AN. There are 2 possibilities. We get a red, which happens with probability 1/2, and we get a black with probability 1/2. If we start off with a red, what is the probability that we do not have 5 consecutive blacks in n spins, given that the first spin is a red? This is the hardest part of the argument.
1.
Nope, not 1. I want the probability we don't have 5 consecutive blacks in n spins, given that the first spin is red. AN minus 1. Because the first spin is red, it's now like we're playing the game with n minus 1. There was a reason we spent so much time on the basketball problem. The ideas behind that are central to the semester. This is the harder case. We now have to figure out what's the probability we don't have 5 consecutive blacks, given that the first one is a black. Well, this complicates things. So what do? We spin again. And we could have a red or a black. Each happens with probability 1/2. What's the probability we don't have 5 consecutive blacks, given that the first 2 spins go black-red? AN minus 2. And then here we have to split again and again. So we have red, black. Each happens with probability 1/2. What's the probability here? AN minus 3. We split again. So we get black, red. Each happens with probability 1/2. This will be AN minus 4. We split again. AN minus 5. So this is red, black, each with probability 1/2. We're running out of space. 0. Excellent. We don't have to worry that we're running out of space. What is the probability you don't get 5 consecutive blacks, given that your first 5 spins are black? This is not a hard probability to calculate. Right? I'm telling you, your first 5 spins are black, and I want to know what's the probability you don't spin 5 blacks in a row. That's why this is the easier thing to calculate. It stops here. Okay. The other calculation is much harder. So this now reduces to a finite problem. Okay? So now we can actually write down a recurrence relation. And we get AN equals 1/2 AN minus 1. Why is it 1/2? Because half the time we spin a red on our first. What's the coefficient in front of AN minus 2? 1/4, also known as 1/2 squared. What's the coefficient of an minus 3? 1/2 cubed. What's the coefficient of an minus 4? 1/2 to the 4th. And we need one more 1/2 to the 5th, an minus 5. We have a recurrence relation. All we need now are the initial conditions. Once we know the first 5 terms, we're done. Can anybody tell me what is the probability you spin 5 consecutive, you don't spin 5 consecutive blacks if you have 0 spins? 100%. What if you spin once? What's the probability you don't have 5 consecutive? Also 1. What if you spin twice? 1. And I do appreciate people using the correct fingers to put up. So you get A0 equals A1 equals A2 equals A3 equals A4 equals 1. Here are your initial conditions. You can now go through and you can propagate and you can calculate A100. Do we want A100? Are we trying to calculate the probability we do not get 5 consecutive blacks? Technically we want to know the probability we do, so we want 1 minus this. This goes down to how is information presented, does that make a difference to you? If I talk about a surgery and if I talk about the mortality rate or the survival rate, I could say the surgery has a 95% survival rate, it has a 5% mortality rate. Which makes you feel better? For most people, they prefer to hear about survival. But it makes absolutely no difference. I can say survival and mortality, they're complementary events, hopefully. There'll be some kind of quantum flux. That's another department. They're the same number. We want to know the probability that you do get 5 consecutive blacks, it would be 1 minus this. So if we do it 100 times, and this spinning is not going well today. So if we do it 100 times, it turns out it's about 81% chance. So Bn will be 1 minus An. B100 is about 81%. So you have about an 81% chance of having 5 consecutive blacks if you spin it 100 times. That is an extremely high percentage. This is why Vegas loves the people who come down with the double plus 1 strategy. Because the double plus 1 strategy will not work. Will it work for individuals? Yeah, a lot of individuals will come down, they'll work for them, it'll give them money, and they will report back, hey, it worked for me. And they love that. Because they can have a bunch of people who make a small amount. The key thing is having those few people who lose big. And the few people who lose big are the ones who will balance it all out. So what I thought I would do for the last few minutes today is talk about how would we write a computer code to attack this problem. We want to simulate this probability. Alright, so what we're going to do is do pseudocode. So for pseudocode, it means I'm not going to necessarily worry about writing down the correct grammar. I want to just write down the structure. So we'll have some kind of function, maybe we'll call it Roulette. And it's going to have 2 inputs. Maybe number of spins and num_do, the number of loops. Okay? So if we were doing this in Mathematica, I would then have my module command over here, and I would end it down here. Okay? And now what I want to do is I want to just record how many successes I have. So maybe I start off, and I'll maybe make count equals 0, and then I'll have a big for loop for n equals 1, n less than equal to num_do, increment n by 1. And end of n loop. So now what we want to do is we want to figure out how to generate a sequence of 100 and tell whether or not we have 5 consecutive blacks. So maybe we'll make the blacks be heads and the reds be tails. And so we want to know, do we have 5 consecutive ones? How could we do this? Thoughts?
Wait.
Okay. So one thing is I could, yes.
Generate a random number between 0 and 1 compared to 0.5.
So good, so I can generate a random number, and if it's equal to 0.5, I can call it a head. If it's equal to if it's less than 0.5, it's head. If it's greater than 0.5, it's a tail. And what I can do is maybe num consecutive is equal to 0. And then what I can do is I can do for j equals 1, j less than equal to 100, j plus plus, and then I will randomly choose something, and if it's a head, I increase the number of consecutive by 1, and if it's a tail, I don't.
You mean j less or equal to num spins?
Oh, sorry, num spins, thank you, yes. Okay, so this is the part where we have to really expand things out a little bit and see exactly how much we want to do. So we've got 1 minute left. So this is the meat of the program. So the question, how do we want to program this? One thing we can do is we can generate a whole string of 100. So we could have a list, and we could just put in a string, and then we could check the list and see are there 5 consecutive ones in it. So one method is generate a string of size num spins, and then check for 5 consecutive ones. And I'll leave this as an exercise for you as to how you could do it that way. What's bad about this method?
Generating
I'm sorry?
It might be slow.
It might be slow, but why might this be slow?
If the first 5 numbers are 1s, I don't want to generate them.
Yeah, if the first 5 are ones, you're going to continue to generate. So this is why what you would probably do is you would do this with a while loop. So what you could do is while num consecutive is less than equal to, is strictly less than equal to 5, and then maybe spin is less than equal to num spins. You could do something like this. And then what you would do is you would do your generation, you would generate your new spin. If it's a head, you would increase the number of consecutive by 1. If it's a tail, you set it to 0. And then you'll break this as soon as you either hit the number of spins or get 5 consecutive heads. So what I'll do is I will send out code on how to do this. I want you to try to write the code to do this yourselves. This is how you can use a while loop. And in terms of programming efficiency, this is great because as soon as the event you want happens, you don't really care what continues. You've already gone bankrupt. You don't want to see how much more bankrupt will you go. The game's over for you. So this becomes a great place to start. All right. Both for programming and the class.